So first quote, Steve Jobs, basically, it's not the customer's job to know what they want. And I've found professionally and personally, when you ask people beyond what they're already familiar with, what they want, it's very difficult to articulate future things other than things like, I want it cheaper, or I want it more efficient, or I want it smaller, or something along the lines that's already been evolving. Likewise to Jobs, Henry Ford asked, if I'd asked people what they wanted, they would have said faster horses. No one really imagined a car. And I think we're on the cusp of that with lighting. So we're really focused as lighting is changing from vacuum to solid state. Okay, yeah, make it last longer, make it cheaper, make it more efficient. But I tried to ask myself, what do I want out of light? And some years back, the thought came to me, when I'm sitting at a window on a nice day, it's sort of that light that comes through the window is what I really want. But beyond that, there's candlelight, and there's fanciful things like light from Mars. And anyway, we'll talk a little bit more as we go. So just briefly about Telelumen, was founded in 2007. We're in Silicon Valley, California. Idea was to create products and services to record and play back light. And certainly at the time, people often say, well, what's recording and playback of light? I hope I'll explain that a little bit. Today, there's a little bit of recognition of it, but it's just beginning to sort of catch. So we're privately owned, small company. Currently, we have products, something called a light replicator, which is the player, and we have Lumen scripts, which are the recordings, and also a recorder, which is basically a spectrometer. I'll show that a little later. And our current products are primarily purchased by research institutions. It's an expensive thing, so we sell to universities, government labs, lighting labs, that sort of thing. But both we and others are working on more commercial versions of the product, and we'll talk a little bit about that as we go. Okay, so let's talk a little bit about this vacuum to solid state. So this has happened a number of times historically. Besides lighting, the last time this happened was with vacuum tubes or valves, if you're from some parts of the world, and to transistors. And at first, we just replaced the existing products, just as we're doing now with solid-state lighting. And we put them in radios and switching systems. But there was that replacement phase, and then there was a revolutionized phase. And I'll argue that the primary revolution phase was the integrated circuit, which was impossible with vacuum tubes. Nobody really thought about that. But that allowed us to do things that were simply impossible or unheard of with vacuum tubes. We're in a similar phase with the visible spectrum and solid-state lighting. We're well into the replacement phase, and we have a range of products that are sort of affordable but not very good, and some very good products that are difficult to afford, but they're rapidly improving, and so it's only a matter of time, I believe, till we not only replace the existing stuff, but we move into this revolutionized phase. So this shouldn't be a surprise to anyone in the call. There's more to light than white. And these are just sort of two extreme examples. I think both of us would argue that, or most of us would argue that both of these are valid. And these are only snapshots. So there's a lot that's going on in between these two slides, and we'll talk some about that as we go. This is some interesting work by some folks at RPI. And this sort of goes to the last point a little bit, but as is probably familiar, and if not, I can explain more later, but I'll just briefly explain. So the heavy black line in the middle of these two graphs is the Planckian black body locus. So that's the chromaticity coordinates for a thermal radiator. And there's some constant color temperature, or CCT lines, that are drawn through the black body. Well, what was done here, and you can read the full thing in the paper, the reference is given there, is basically the subjects of the study were able to adjust the chromaticity along the CCT lines. And they didn't necessarily get the exact details of this, but they had a knob where they could adjust along CCT lines, and they were asked to basically stop on the point where they thought it was white. And they did various things in the experiment to make sure that they tried to control for people just repeating things from previous times. But the bottom line is, when you ask people to tell me what the color of white is at various color temperatures, they seldom pick anything on the black body line. Yet we struggle mightily we in the lighting industry, to make things that are on the black body line, or sometimes, as is shown in the right-hand graph, black body line, because they give us better lumens or better efficacy. And the point is that if people have a choice, that's not what they call white. And the speculation is, and this is more my speculation than theirs, but I'll show some pictures. The speculation is that it's because filtered daylight, so the sun through the atmosphere, follows these curves that people say. When we get to low color temperatures, we like pinkish, yellowish skies and so forth, and not so whitish. And we've just biologically been conditioned to believe that that's white. So the point here is A, that it changes during the day, and B, that being on the black body is not necessarily the ideal spot. Okay, here's one example. This is a picture of a sky. You can barely see the moon, actually, that is, through the sky. This was a picture near where I live. It probably doesn't come through all that well from a color fidelity point of view on your monitors, but this sky, A, was just beautiful. No one would object to this light, but it's not a normal color that we see from illumination systems. And even more to the point, it happened to be I was outside with my wife. Her skin looked beautiful. It was really incredible under this light. And I took this snapshot because that's the kind of light I'd like to be able to have when I want it. Okay, so we're used to light as entertainment, and I really want to make a distinction between, and while entertainment is valuable, entertainment is when we're sort of looking at the light itself, not experiencing it. And this is a different thing than illuminating people with different spectral lights. And just as an example, we see on the left-hand side a nice picture on a monitor. It looks very good, red, green, blue. That works great. But if you sort of look at the picture on the right and you see the boy that's illuminated by a TV screen, it looks terrible, looks dead. And so while RGB is great when we're looking at it, it's really not adequate to make good illumination systems. So just a brief summary kind of point is that light's more than turning things off for RGB. There's the spectral variation, the temporal variation, the spatial variation, and the distribution of light. On that distribution point, the sun again gives us, or daylight gives us, a good example. We have both the collimated light from the sun, and which moves across the sky, and we have the diffuse background light. And if you think about the way we do illumination systems in general, it's a combination of those. We have reflector lamps that focus light relatively parallel to highlight objects, and we have the background light to diffuse things. So all of these points are important, and solid-state lighting allows us the ability to control these to a much higher degree than we ever could before. Okay, let's look at some spectrums. So some pictures here on the left. You see a halogen bulb, nice, smooth spectrum. All the colors are represented. It's one of the reasons we like the light from halogen bulbs. CFL, on the other hand, which is like other fluorescent and discharge lamps, have these spiky spectral lines. And in my mind, somehow, the image comes of fingernails on a blackboard, sort of looking at that CFL spectrum, screechy, versus music, for example. On the right-hand side, we have some LED spectrum. And the one at the top is actually pretty good. It's close to that halogen spectrum in general shape. The middle spectrum is not quite as good, but not terrible. The lower spectrum, the one that says Toshiba 8N, that's pretty poor in my view. It's got sort of an inverse, lots of blue light, not much red light. That's easy to make high efficacy lights out of that lower spectrum, but not really very good color quality. And in my view, if that's all we do with LEDs, we're not going to get very far. And of course, there is better things. So, okay, let's talk a little bit about these replicators. So one of the things in sort of understanding how technology changes is to look historically and see if there are other analogies. And we already talked a little bit about the vacuum tube, the transistor, but here's this replicator idea that has come up over and over again historically, from the printing press and camera to the Betamax and MP3 players. And one of the common things that occurred when looking at these is that initially people were looking for a 2x improvement, and sort of at best. And most people said, we don't need such a thing. It doesn't matter. We don't need to replicate things. We simply do what we've always done. In fact, rather infamously, Thomas Edison was loath to get into the music business, and in fact, GE never became a significant presence in the music business, even though it invented the wax cylinder audio recorder. He thought it could be used as a teaching aid. But his reasoning, not music, is that people would go listen to music the way they always did. They'd go hear it performed live. There was no reason to listen to it individually. And of course, today that sounds ludicrous, but that was the deal. So what we think about, and if you look at the lower right hand picture, light replicator, that's Telelumen's thing, what we think is that people will play back light recordings, that lights in general, or luminaires in general, will be light players as opposed to static fixed color temperature kinds of things. So let's talk some about this light recording. We call these things lumen scripts, but they're light recordings, and they're made with, they could be made with an RGB system, but as we talked earlier, that's really not enough fidelity. At least we don't think so. So we use spectrometers to do the recording. Ideally, you'd use a hyperspectral camera, which sort of has a spectrometer at every pixel. Currently, those are very expensive, but in reality, if you simply took the existing camera technology and had more filters inside, which could be done by the makers of those sensors, you could make a high-resolution spectral camera. It doesn't have as high resolution spatially, but you don't need super high resolution spatially for illumination. But what you do need is a lot more spectral and intensity levels. So at any rate, the first things we recorded were static things like an incandescent bulb, and then we recorded dynamic things like candle flames, and then we started moving outdoors and doing more interesting things, as you can see on the list. Let's talk about these a little bit. First of all, here's the setup. You can see in the background there's some software runs on a laptop or other device, and a spectrometer example in the lower right-hand corner. And this is the actual recording of candle flame through fiber optic that connects the things. And here's some software that also is available from us, but other people could make such things, which takes these recordings. And really, once it's a digital file, which is what comes out of the spectrometer, it can be manipulated really in the same ways you would manipulate audio files or video files to create content. And these are just some example screens. So first one we did outdoors was Mount Hamilton. We call this the warm-up because of climbing Mount Fuji, which I'll get to in a second, was a much bigger deal. So this is a mountain in San Jose, California. You can see an observatory if you look closely on the top of that hill. So we went up there very early in the morning, and if I can just walk you through the pictures. So upper left is just a picture of the sky, obviously. The upper right, you can see the sighting tube, and just in the center of that, you'll see the sun on just ready to come up on the horizon, and you can see the color of the sky at that point. Lower left picture is the equipment, which was later in the day, of course, and it's basically a telescope mount that's going to drive the sensor across the sky, following the sun, and there was our luminographer in the lower right-hand corner preparing for the day there before sunrise. Okay, and let's look at some snapshots. Now, again, we recorded continuously, but this is some snapshot information to sort of illustrate the variation that goes on. We talk about sunlight all the time, and if you look maybe at the upper graph, the blue one, first one, it's actually 2:45 in the afternoon, which is around the time when D65, the daylight locus point, was chosen for, and you'll see that that looks reasonably like the D65 locus for those of you who are familiar with it. But as you go through the afternoon, and this is just over 4 hours, you look at the variation in both spectrum and intensity, and that dotted red line that's at the top is simply the lowest red line, the one that occurred at 6:38 p.m., scaled to be the same as the first recording. So the point being that the spectrum has almost flipped within a 4-hour period. And this was a nominally cloudless sky. I mean, there were some misty clouds during the day moving through, but there was just tremendous variation. And which is just normal. We don't notice it because it happens slowly enough, but this was a very nice day that had this variation. And what was even maybe more interesting is when you looked at the video being played back, it didn't just go in one direction. So it looks like it's moving in one direction here, and it is in a gross way moving in one direction. But there were, over periods of minutes, both the color and the intensity was going up and down in a very nice way. And if you were to look at someone's pupils during that time in their eye, you would see they were contracting and expanding over this time automatically. And that input to your system, we believe, is one of the reasons why you like sitting by the window. Of course, you like looking outside, but even if you can't look outside, you still like that slight variation, and that's completely opposite of the way we try to make lighting as it is. We turn the lights on and they stay at a fixed thing. In fact, we work really hard to make them be fixed, but that's not really the way light works in nature. And so we think, again, these recordings or elements of these recordings compiled into content would really be the way electric lights should work if we had. Okay, so again, here's a little bit of some graphs and ones that we're maybe somewhat familiar with. There's the CIE locus. This is the 1931, and please, I know there's newer ones, but this was just convenient to show. And there's a blow up on the right-hand side, which shows, again, this variation. So you can see that the chromaticity, now there's no intensity information here, but the chromaticity is going up and down over time. It's not just going in one direction. Okay, bigger plans. We sent one of the guys, in fact, John, that you saw earlier, a luminographer, to climb to the top of Mount Fuji in Japan. And we chose Fuji because it was exotic, and also because for Japanese people, climbing to the top and watching the sunrise is a really big deal. They try to do that once in their life at least. So we thought we'd climb up there and try to make a recording. And so this was at the base of the mountain, and this is just an interesting shot. This is actually right about near the summit, but this is the shadow of Mount Fuji. That shadow is about 60 miles long. It's huge, and sort of near the tip of the shadow is where Tokyo is. You can also see, and again, this doesn't come through great on the monitor, but you'll see that there's a bunch of junky air in the lower 2/3 of the picture, or the lower 3/4, and then you'll see some really pristine air that's above that, which is mainly where we were doing our recording. And this also, we happen to get the moon in the sky, so the sun is, of course, behind us in this picture. There's our equipment. It almost looks like you're on the surface of a moon or something. So same equipment that we took up to Mount Hamilton, we took there, and being Japan, we could leave it set up overnight. And, well, of course, it was also the top of a mountain, so nobody stole it, but we tried to put a little sign on explaining if somebody came across it what we were doing. So John spent like 3.5 days on the top of the mountain there. And this is just an indication. This is on the top of the mountain, sort of where it was being taken. So right at the crater that's at the top. And here's what we were doing. This was the first stereo recording we made. So again, we carried that telescope mount up there. One part was basically tracking the sun, and another spectrometer was recording the north sky. So we got both blue sky information and sunrise, sunset kinds of things. Again, here's the equipment position just before sunrise. Sun's just breaking through, and again, color and intensity variations. Here it's really coming up. There it's in the sky. And again, we were making continuous recordings, but just some snapshots. And like Mount Hamilton, here's some snapshots shown. And again, variation in color, temperature, and in intensity. And one point to note, if you look sort of the gray line, I'm not sure if it's gray on your screen, but the gray line there, the color temperatures we recorded things up to about 10,000 Kelvin. And I think most people would say 10,000 Kelvin is crap. Nobody would want light like that. But if you have the full spectrum, it's really not bad light. And I mean, this was in fact wonderful light. And partly what I'm saying is we should look beyond our traditional boundaries we put on color temperature and say if it's done right, we can really have very wide range of color temperatures that are useful for things. Okay, here's another recording. This was done in Valley of Fire, Nevada, US. So you can see here we have these lots of reddish rocks. So that was kind of an interesting one. This was done just this past summer, and that's sort of the background. And whoops, before I go there, let me back up one slide. I'm going to drop out of this PowerPoint and show you a video, time-lapse video of what's going on here, this recording with a 5-color solution. And let me see if I can bring this up real quick. So hopefully you're seeing this recording. So if you look in the lower right-hand side, you'll see chromaticity being traced out. This is basically 90 minutes of sunrise in this area. So the upper right graph is showing the color temperature cranking up over time, or where the color temperature is. It's also showing the time that's available. The 5 colored circles that you see, blue, red, green, so forth, those are the 5 colors that are in this solution. And on the left-hand side is the actual recording in red, and then the 5-color solution in black. And these solutions are basically solved by software that we make, although others could make it. I mean, it's normal photometry kinds of things and color science. But it does a best fit. So very high color rendering, very good efficacy, and again, you can look at the variation that occurs in the light, even this nice little circle, squiggly thing that it's doing right at the moment, and almost none of this is actually on the black body. Okay, I'm going to exit out of this guy and go back to our main presentation here. There we go. Okay. So as mentioned, you need about 5 colors. Here, there are the 5 colors. Here's the example recipe, and that's the ones that were used in that previous graph. Think falling prices make having more LEDs. I think the LED count in lights will go up, not just the number of colors, but the total number of LEDs. As prices come down, similar to the way prices of transistors came down, nobody tries to minimize the number of transistors in their iPhone. In fact, we try to jam as many in there as we can because that's the magic. And I think that same thing will happen in with lighting. Showed this picture. That's the one you saw the movie of. Here's an example playlist. So this was one that we did this is a stereo playlist that can be stored in the Luminaire. This was one that was actually we gave, sometimes when I do these talks, so there's live demonstrations, and this was a particular playlist that was used, and you'll see there's some stereo recordings, candles, different kinds of candles and so forth, and the Mount Fuji stuff, which you saw. And we even have, music tracks. And in fact, I think that's another thing that will happen, probably, for sure, music and probably also video tracks will be available to accompany these illumination LumenScript tracks. So, for example, if you had, sunrise kinds of things, you would have birds chirping in the background, leaves rustling, wind blowing kind of thing. And I think that the real message with illumination is it's a little bit maybe like 3D in movies. A little bit of it is good. You don't want to bang people over the head with color changing and too fast changes or too loud music. But I think just as movies started out silent and added soundtracks, I think light will start out, is silent now, and will have soundtracks that go with it that are appropriate for the light. Okay. Here's some other examples coming up. So these are things not from Telelumen, but that are on the market that do some of these kinds of things. This is a slide, and the reference to the link is there. You can go look. These are Philips light therapy products, they call them. They say that they're certified, they're clinically proven and certified by the National Sleep Foundation. I'm not vouching for that. I'm not agreeing or disagreeing, I guess, but they're claiming they have some science behind this, and they have different ones that have to do with circadian health. Some are just light bulb kind of things that are bright lights, the first couple. But the latter one, this HF3520, is an LED system that allows you to set the time you want to wake up, and as you can see there in the picture inset, change color temperature. Here's a product from Japan. I realize you can't read this, at least probably most of you can't, but this is a 5-color luminaire that Toshiba sells in Japan. It has not quite the same 5 colors I showed you earlier, but a similar complement, and it comes with some pre-recorded things. It's typical in a Japanese home to have a large luminaire in the middle of the room still. That's you know, not as common in the US or Europe, but at any rate, it's done this way. And they have these pre-recorded things they call, I've translated, you can see above and below the Japanese, vivid, theater, healing, studying, relaxing, sleeping. The sleeping one confuses me a little bit. Now, again, the colors don't translate perfectly because they have a 5-color system and we're looking at this all on RGB systems, so it's been distorted a bit. But nonetheless, the sleep thing is on the greenish side. I don't really understand that, but anyway, that's their thing. This is another Japanese product. This is from Sharp, and this is, if you look sort of in the middle of the page here, this graph is basically time. So you can see it goes from 5 a.m. to midnight. And this is changing both intensity and color temperature. Now, this is the output of the luminaire. So you'll see during the middle of the day, it looks like it's not producing very much. That's because the daylight harvesting sensor, which they talk about in here, but you probably can't read, the daylight harvesting sensor is kicking in, so it's turning the light down. But you'll notice by the coloring in the picture, or in the graph here, that it's sort of high color temperature light during the middle of the day, and then in the very early morning and in the, later in the evening, the color temperature is shifting. So this is, I think this is quite a good example of a circadian healthful light that also looks at energy consumption. Again, this is only available from Sharp in Japan. I'm not really quite sure why neither of these products are available in the US, but they're not. But I travel to Japan often and look at this kind of stuff. Okay, here's some other products. This was a vertical lighting example, which I think is really quite good. So you can see during the day on the left-hand side, the windows are lit, but in the evening when the windows are gone, you can have light. This is actually brighter than it would appear, but because of just the way the photograph was taken. But I think large vertical panels are another sort of useful tool for us. This is a very interesting thing. This is from the Fraunhofer Institute in Germany. I actually visited this lab and met with these guys. So the entire ceiling, so we talked earlier about there's spatial and temporal and spectral changing. This really does a good job. The only thing this doesn't change is the light distribution. So it's all diffuse light as opposed to some directional stuff. But it's really cool. The clouds ceiling moves across the sky, light levels change during the day. Very impressive thing. Any of you happen to be in Germany, it's worthwhile taking a look at. I've heard someone's trying to commercialize this product, but I'm not aware of any commercial versions of it. One other brief thing that might be of interest here, sort of a side note, the Fraunhofer Institute also owns the MP3 codec. So one of the ways they got to have lots of money to do all this cool stuff is they get a little bit every time somebody does something with MP3. Okay, here's some other, again, just large forms and shapes. And I think these large forms and shapes are something that, again, solid-state lighting can do, and it helps us, again, to, in conjunction with natural light, really stretch our physiology and psychology during the day for these changing shapes and forms. One other is a book, and it may have gone out because I sent this to Stan a while ago, but so you may already have seen it. This is a book that I read recently as just the title or cover and table of contents. I think it's really cool. It really gets at the kinds of things that we talk about at HCL, and I encourage you to read it if you haven't already. Okay, a couple summary slides and I'm done. View is the last pillar of vacuum technology is giving way to solid-state devices. Visible spectrum is far more useful than turning it on and off, white light or RGB. I think light recordings, light compositions, and light playback are newly possible and pretty cool stuff. Window seat brings changing illumination and view. So yeah, we get the view, but even if we don't get the view, we get the changing illumination. And daylight changes by the time of day, place on Earth, and season, which is probably not a radical thing for people on the call here, but our electric lights don't do anything like that. And we can do it with solid-state lighting. And I think really one of the core values of solid-state lighting is the ability to reproduce these various changing aspects on demand for circadian health and enjoyment. And just as a final comment, even a little bigger view than the circadian health is that I believe the impact of light on the 21st century will be equal to the impact of radio frequency on the 20th century, which it's difficult to overestimate the impact of manipulating the radio frequency spectrum. But I think we're really on the cusp of manipulating the visible spectrum in a similar way. And in fact, if for those of you who are history buffs, if you go back and look at Marconi and Hertz in the late 1800s, not much was thought of their wonderful invention at the time. And it just, manipulating the electromagnetic spectrum is just a huge thing, both for its data capabilities and its impact on humans, our ability to see the visible spectrum. So with that, I'll conclude. Thanks for your attention, and if you've got questions, I'd be happy to try and answer them.